Hello everyone. So in this video we're going to be talking about an application of infinite series and really more a form of infinite series called power series. And so that form can be seen right here, just like when we talked about geometric series or p-series and stuff. This is just a series of a particular form. Notice it is a function of x. It's also a function of this constant, which I will call c. We call that the series is centered at x equals c. And we also have the value n that shows up within the series as well. So the cool thing about power series is they can be used to approximate functions. And I know what's going through your head right now. You're sitting here, you're saying, Dr. Williams, it's the Sunday after prom. I've had the most amazing prom weekend. How can I possibly just cap it off with one of the most thrilling math videos I've ever seen? And it is right here. It is in talking about this because this is a really, really cool concept. And it's also how your calculators work. It's how they calculate various functions. It's also how, if you wanted to just ditch your calculator, you could calculate values of some fairly complicated functions by approximating them with infinite series. But anyway, they're really cool just because they allow us to represent any kind of function, at least in part, with an infinite series. So some other neat things we can do with power functions is if we apply the ratio test to them, we can find something called its radius of convergence. And that's basically the same thing we did before when we applied the ratio test to find our interval of convergence. So in this case, a radius of convergence is just some constant distance away from this value c. That's why we say it's centered at c, of which this is a suitable approximation for this function. So if we think about this kind of like a number line, something like this, we have where the series is centered, that's x equals c. And then to some radius, to the right or the left of that is what's called our radius of convergence. So it's basically saying C is like a bullseye, and if we're anywhere within this radius of convergence R, this is also going to converge as well. So a series approximation for a function, but maybe an approximation that only works in a specified range, not necessarily for the entire function. That's also why we use approximate. All right. So when we talk about it being centered at C, this is exactly what I was just saying before. It means that this series approximation to this function is only valid within two types of bounds. Now these bounds are going to always be a distance r away from our value c. That's why it's called a radius of convergence, because imagine it again like a bullseye, kind of like a circle extending outward. All right, so what happens at power series is that, well, they always converge at x equals c. That's one cool thing about them. So if we plug in the value x equals c in for f of x, this series approximation will always converge on a number. It'll always give us something that we can use, which is really awesome. All right. So they will also do this. They'll either only converge at that value, which means that the series diverges everywhere else. So in that case, we have no radius of convergence. There's no kind of bullseye region for x values that we can get convergence. I basically have to hit it right on the bullseye, which is right at x equals c. Or it converges over some region, and we can do the ratio test to figure out what this interval of convergence is. Notice we have 4 different criteria. Again, these are dependent on those endpoint checks we do, depending on whether or not the series converges at the right or the left endpoint will dictate what type of bound we have from the list right here. Or the third option is it converges for every single value of x, and this is awesome. We have an infinite radius of convergence, so no matter what value of x we plug in to this power series, it's gonna do us a huge solid. It's gonna come through. All right. It turns out a lot of functions that we use in our calculators, like e to the x sine of the x cosine x, they do have infinite radius of convergence, so they're very fun functions to work with in that regard. All right, so let's take a look at this. Let's look at this power series, and this is actually a power series centered, obviously, at x equals c. This is the form it's in, but it represents a geometric series. Notice that in this case, that sequence a sub n that was in the power series on the previous slide, well, I'm just going to say that's just the constant a, okay? It's actually not a function of n in this case, and I'm doing that just so we can analyze this series from 2 different points of view. One of them is a geometric series. So notice that value a, that's the constant in front of our r value. In this case, r is x minus c. And if we count out the first 3 terms of that series, we get something like this. Now, if this x minus c is the value for r, let's assume that x absolute value of x minus c is less than 1. Remember, that's the condition for a geometric series for convergence. If you're a little bit, if you don't remember geometric series too well, I suggest going back in one of the videos and maybe rewatching that before coming back to this spot in this video. But if I ask, what does a above power series converge to, what would you tell me? Remember, think it's a geometric series, so pause the video and try to tell me the answer. Okay, well, the answer in this case is, again, if it's a geometric series, this value out front a, well, that's our a in the geometric series. And you like that? I had the audacity to take the screenshot, before we corrected the autocorrect stuff in Word. And that's just assigned to the production value of these videos. I started this year. I just gave you a promise that I'd make you some good calculus videos that helped out, but nowhere did I promise that I would do any sort of editing, or that they would be professional in any way, or that if I made a mistake, I wouldn't just keep going, because that time is valuable to me. So that's what you get, and that's what we have right here. There you go, red line, green line, awesome. Okay, anyway, so in this case for the geometric series, the value a is just the a in the geometric series, and r is x minus c. Remember, c is some constant, and we plug in a value for x. X minus c just becomes another constant. The big thing in the geometric series is, remember, that value for r can't be a function of n, and neither x nor c are functions of n, so this is a suitable value for r. So therefore, a over 1 minus r is given right here, and if we rework it, basically what we got is that this function right here, or this power series, is actually a representation of this particular function. So if we plugged in a constant for a, and we plugged in, whoops, I shouldn't have gone down that far. Pretend you didn't see that. If I plug in a value for a, and I plug in a value for c, and a value for x, I can completely approximate that value with this function. Now remember what I said, all power series converge when x is equal to c. So what I want to find out now is, okay, well, what x values besides x equals c can I plug into this series to get it to converge to what the function on the left is? So I want to find its interval of convergence. So why don't you guys pause the video, try to do that right now. All right, so if you go ahead and do that, we just apply the ratio test again to our series. If we do that, we just get this, which just leads to, wait a second, we've actually seen this somewhere before, just very recently. Do you know where you've seen absolute value of x minus c less than 1? All right, well, remember we said this thing was a geometric series, okay? So we knew that the absolute value of x minus c had to be less than 1 for this thing to work. But the cool thing we get here, and the reason I wanted to show this, is because generally when you're going to find a radius of convergence for a power series, it's not going to be a geometric series. You're going to have to do the ratio test. But I wanted to show you guys, in this case, the ratio test actually comes up with the exact same result as we know from a geometric series. So that's just a little thing that makes us smile. So if we solve this inequality, we get this. Remember, this looks exactly like the concept of radius of convergence. In this case, the radius of convergence is 1. Our x values are valid anywhere between -1 and 1 away from c. So if we drew a number line of x values, again, we'd have c right there in the center. And then this would be c minus 1. And then this is c. And then c plus 1 would be this line right over here. So again, you can see that our suitable values are going to be separated by a distance of 1, which that distance is, again, this radius of convergence right here. All right, so anyway, it basically tells us that if we're going to plug in any value for x, if it's within 1 of c, this series approximation for this function will converge. But if it's anything outside of that radius of convergence 1, it will diverge, okay? And if we do our endpoint checks, just plug in our endpoints c minus 1 and c plus 1 into this series right up here. You'll get that in both cases you get a divergent series. So really the interval is this interval we have right here, with no less than or equal to signs on the inequalities. All right, so I get it. At this point, you're sitting there, and you're going, Dr. Williams, it's the Sunday after prom, in which case you might be watching this video possibly in not the year 2016. Then I have no idea what day it is. Let's just say it's some day that I assign this video. Anyway, but for now, all right, it's Sunday of prom. I'm really having trouble following what you're talking about here. This stuff looks like hieroglyphics. I don't get it. What are we doing again? So that's totally normal. Seeing some of this series stuff can be difficult to process the first time. So let me give you kind of a visual representation of what we're talking about here. So notice right here, I've plotted the red line, that function that we found this particular series converge to. Okay, so the red line is that function. C is where we're going to center the series. So notice that if I move the slider for C, a couple different things move. Well, first of all, the function changes because it's, that's C is right here within the function. So if I slide that, of course, the red line is going to change. But what you notice is there are these two dotted black lines and this one dotted purple line. The dotted purple line is the line x equals c. So that's what we're centered around. And these two dotted black lines represent our interval of convergence. Notice they are one unit away from each other. That's that one radius of convergence that we have. This value a, that's just something else in the function. It can be used to change the red line if we want to do that, but let's just keep it, just at that value. But really what I want to do is mess around with moving this value of c around, all right? The next thing I want to do is show you this. Here is the representation of our series. Remember, this series was an approximation for this function. So if we graph this series, then it should look a lot like our red line that we have right here. So if I turn this graph on, you see immediately, well, that doesn't look very much like the red line at all. But notice what I'm plotting right here. I'm plotting our series, but it's a function of I can't put infinity in Desmos up here, so I put the slider n, and that's something that I can go up. So if I want to approximate an infinite series, I just drag that slider as far as I can to the right before Desmos crashes, which it inevitably does, which is actually kind of funny to see sometimes. But anyway, if I do that, I'm going to get this kind of pseudo-infinite series approximation of this function. So again, starting at n equals, or capital N equals 0, all I get is a straight line, okay? But notice that straight line goes right through where my function value is at C. Remember, I told you power series, no matter what, converge at the point they are centered at. So again, but this one, it doesn't look like it really converges to the red line anywhere outside of that center point. But let's make n go up a couple steps. All right, so we did that. So what do you notice? You notice that the blue line now is matching the red line as we put more terms in our series, and it's matching it much better within these bounds of these black lines. Remember, that's our radius of convergence, or our interval of convergence. It's matching up much better right there. And so if I drag this all the way to something high, notice that again, the blue line is now pretty much perfectly matches the red line, but it only does that within our interval of convergence, which was a radius of convergence away from the point we were centered at. So I wasn't lying to you, all this stuff was true. This actually is a good approximation for the red function, but again, it only works within that interval of convergence. So let's also look what happens when we go outside of this interval of convergence. So I'll drop back. What I'm going to do here is add another slider for this point B, which is the green line. So if I move that slider around, I can choose an x value that is either inside our interval of convergence or outside our interval of convergence, like right here. So let's look right here, okay? Let's do this. Again, we are starting at n equals 0 up here, so we're getting the crudest approximation of our function. If I try to evaluate f of b, now realize I said f of x was this series, so if I plug a value, if I tell Desmos evaluate f of b, that means plug the value x equals b into this series and add it up, capital N number of times and tell me what I get. All right? So if I just put b to some random value that's within that interval of convergence as it is right now, and I start making my terms in my series go up, look what happens to that approximation for f of b. It just goes 3, 3, 3, 3, 3, 3, 3. Eventually, it just doesn't change. Okay, look at that again. We start at n equals 0, and it's 2. It's a crude approximation. It only has one term. But when we add more terms to the infinite series, the approximation gets more accurate and more accurate and more accurate and settles on a number. So what does settling on a number mean? It means converging. So again, if we pick an x value, anywhere within our interval of convergence, this series going out to enough terms gives us that exact value, and it converges on something. All right, so now let's drop our terms back, and let's put a value for b. Notice I'm dragging the green line now outside of our interval of convergence. So let's try to use this series approximation to calculate what, for example, f of b is when b is 4, which is outside of those two bounds. Well, okay, I start out with actually the same thing I had before. It equals 2, but now notice when I add more terms in my series, look what happens to that number. It's just getting higher and higher and higher and higher, and it's growing without bound. Now, what does that remind us of? If something grows without bound, does it converge? No, it's not settling on anything. It's diverging, okay? So, I appreciate the fact that this stuff is sometimes difficult to get, but at least for me, seeing the visual example like this is really helpful. So we will go over some more of this stuff again, some more specific types of power series in the next video, Taylor and Maclaurin series. But until then, check out that next video and come to class with questions about this stuff.